I wanted to talk today about how we're using generative networks to push forward the frontiers of atomic scale characterization techniques. And before I get started, I want to say that strangely, I'm actually the least qualified person on the team to talk about generative networks. But this work has really been done by two fantastic grad students. One of mine, Jahao Lee, who just graduated and is going to Cornell for his postdoc, Abid Khan, who is a machine learning expert, and Brian Clark, his advisor, who's in our physics department here. And really, we worked together because we wanted to understand this question, right? How can we use generative AI to help us understand materials at the atomic scale? And generally, my group is focused on characterization with scanning transmission electron microscopy. So we're often trying to look at structures like 2D materials to understand strains and defects that occur in them. About half of my group works in 2D systems, either looking at the atomic scale or trying to connect the structure and properties of two-dimensional materials. But we also do atomic scale characterization of other things, where we try to develop new characterization methods to study them. So for example, trying to image molecules, single molecules at atomic resolution, and trying to look at atomic or electric and magnetic field within materials at the atomic scale. So these might not be things that you think of when you think of generative AI. But before we get to that generative stuff, I want to tell you how we normally generate an image experimentally. So the tool of choice in my lab is scanning transmission electron microscopy. So we're taking an electron gun, we're making a high energy 60 to 300 kilovolt electron beam, and then we focus that down to about the size of an angstrom and scan it back and forth on our sample. Normally, we collect the scattered electrons, and that's this annular dark field detector right here. And we like this because it's a quantitative technique. You can get what's called Z contrast in a material. So that means that the brightness of your local contrast is related to the Z number, approximately Z squared is what people say. So for example, if you're looking at graphene, it's all made of carbon atoms. So all of these bright dots is the location of an individual carbon atom in the material. And this technique can be really powerful when it's applied to any material, but two-dimensional materials in particular, because we can, for example, take pretty large images. So this is actually, it's 3 by 3, so it's a tile of 9 individual images, but they're all atomic resolution. This is a material that's tungsten diselenide alloyed with tellurium. And when you zoom in, you can really see the wealth of information contained in these scanning transmission electron microscopy images. So for example, I told you this is alloyed with tellurium. Tellurium is heavier than selenium. And so you'll see it pop up as these bright dots, 1, 2, 3, etc. And you can really just look at this specific microstate of the system that you're studying, which is really rare at this length scale. You can also see other features in this, like voids. So you can see there's a missing atom right at the center of this little trifoil sort of feature. And, you know, when I look at images like this, I immediately wonder, oh, what if we could just really mine all of this wealth of information that is present? What could we learn about materials that we couldn't learn before? And this is especially a powerful technique in two-dimensional materials because you're only looking at one atomic layer in projection. So you're always looking at just 1 or 2 atoms. And so you can see right away when you have an individual plate defect, if you have a grain boundary, or you can look in cross-section and look at single interfaces. And so in these systems, we like to study them not just because of their applications, but because they represent a new opportunity for material science to understand defects in interfaces, really with single atom precision. And even though this is a potentially really powerful approach, when people do nanoscale analysis on this or basically any other system, they're usually looking at and analyzing images with just 100 or 1,000 or maybe a few thousand atoms in it. So this question of how to actually scale up and take advantage of this large atomic resolution data set is a challenging one. I'm just going to check that there are no questions. Oops, no questions. Great. Nothing catastrophic has happened. Okay, going back to full screen mode. Uh-oh. Let me go right here. Great. Okay, good. And so, like I said, there's really all of these studies that have been done on the scale of a few thousand atoms, and very quickly you can imagine that that's not going to cut it. The cutting edge of 2D materials synthesis is the millimeter scale these days. You can exfoliate really high quality two-dimensional materials. And then, you know, they're putting them next to actual rulers with millimeters and inches, which is wild to me as someone who started in this field where making something 100 nanometers across was really impressive. But when you try to look at the properties of these materials, like over here with photoluminescence, you can see that even though people can make these really large flakes of 2D materials, they're really not uniform in quality. So this dark patch right here represents, we think, and actually we know to some extent from TEM studies, a high concentration of defects locally in the material. So, what I'm going to tell you today is a little story about our journey and how we started down this path where we wanted to create realistic atomic resolution STEM images using generative networks, and how those have been really useful for us to scale our work up so we could locate and classify defects on this million atom scale. So to introduce this work, I first need to talk about what generative AI is. And I think generative AI it's kind of a great time to be giving a talk on it because it's leapt into the popular culture just in the past few months. So the idea is that generative AI is a type of machine learning that learns patterns from large amounts of data, as most ML does. It generates new original content, and that content can be anything, but most commonly, I think, so far, generative AI has been used to make either text or images. And really what it is, you're training a deep learning model to understand something about the underlying structure or characteristics of some sort of data set, and then produce novel outputs with similar attributes. So for example, if you feed a bunch of Monet paintings into your generative network, then you can later come back and say, I'd like you, and then separately feed it a bunch of images of llamas. Then you can come back and separately say, please give me an image that is a picture of llamas in the style of Monet. And you'll get back something like this. Yes. You can do other things with generative AI. So the most commonly talked about AI is ChatGPT these days. The New York Times cooking section used AI to write Thanksgiving, used ChatGPT to write Thanksgiving recipes. And what I would say is the performance of generative AI is spotty. So for example, some of the newsworthy applications of generative language networks include things like, okay, a lawyer makes a court filing using ChatGPT, and then you can see it did not go well. And then other things in the news, you might have heard about the new Bing search engine that uses generative AI. And then the New York Times had their tech columnist converse with the chat side of Bing and was quite disturbed by the interactions that he had with it. So, you know, I feel like generative AI right now is emerging as this potentially really, really powerful tool in our toolkit to just operate in everyday life and possibly science and engineering. But it's also one where both the potential for great things and the potential for terrible stuff are emerging at the same time. In the context of material science, there's really a lot that generative AI could do. And so here's just a list of a couple of things. My favorite on this, and what I'll end up talking about today, is applications in data augmentation and virtual screening. So somehow using generative AI to help us look through data more quickly, or make data that can help us with something. And other applications of generative AI include things like accelerating materials discovery, predicting materials properties, designing tailored materials, etc. I also actually use generative AI to make this slide, so all of the text as well as the image came from one of these generative AI networks. So it really is something that does know a little bit about science and has been trained to understand to be able to spit out text and images that relate to what science can do. But if you try to actually use generative AI to do any sort of science, you quickly run into problems. And so far, really, people have done non-generative types of machine learning. So some examples include using neural networks for defect identification, trying to make their images cleaner by denoising or deconvoluting them, and then doing things like maybe in-painting data, where you acquire part of an image and have the AI fill in the rest. And these are non-generative types of approaches. If we then go to just like one of these online image generators and say, hey, we like an image of atoms in graphene, you might get an output like this. And given that the actual experimental image of graphene looks like this one on the right, you can see, getting things close in terms of matching the black and white, having a generally crystallographic pattern really isn't going to cut it when we're trying to do actual science. And push that forward. So what could we do? What would be the dream of something that we could do with generative AI that we can't do today? And maybe a low-hanging fruit in terms of an idea of an application would be some sort of self-driving or autonomous microscope. And so this could be something that you could load a sample, it would align the optical conditions, find regions of interest, acquire, and then process the data. And when you actually look at this list, a lot of this we can do already. So for example, even without generative AI, we can start to do a couple of these steps on the autonomous TEM list. So for example, the first step in the self-driving microscope is the ability to be able to align the instrument and take data by yourself. We already have codes to do this, in part because there are automatic alignment scripts now built into the TEMs today. So we can do things like use basically Python coding and something called PyWin Auto to connect a bunch of these automated scripts so that you can step the stage around, let the stage settle a little bit so that you can acquire a nice drift-free image, focus, adjust the aberrations in your image, and then acquire. And you can just keep doing this over and over. And just by writing a script like this, you can very quickly get to the point where now you need some sort of artificial intelligence to analyze the data. So if you run one of our scripts like this to acquire data on a 2D material, you can acquire about 200 images in a workish day, so over the course of 9 hours. And those 200 images, if you take them at atomic resolution, will span about 300 by 300 square nanometers, overlapping so that they can be tiled together, and about 3 million atoms. So that you can see the limiting part of this self-driving microscope isn't the driving part, it's the analyzing part. How do you find regions that are interesting and process the data somehow to extract something good about, something useful about the data? And what might be useful in terms of understanding this material? Well, I told you that we had this material, tungsten ditelluride, or tungsten diselenide alloyed with tellurium. We could look at point defects in this system. And so the most common types of defects in this material all lie on the Chalcogen-site. So this is kind of the structure looking top down. The grays are the tungsten, orange is the selenium, and those kind of alternate as you go around this hexagon. If you look at a Chalcogen-site, you could have one vacancy in that there are normally two seleniums there, so you could have just one, or you could have a divacancy, so both seleniums could be missing. And then in our doped system, you could also replace one of those seleniums with tellurium or both seleniums with tellurium. So we call these 2Te, SETE, SV, DV defects. Okay. So the first thing we wanted to do is figure out if we could train some sort of neural network to understand these defects, to locate them. We used a convolutional neural network. It's a ResUnet structure. This is a supervised learning technique. And the way that we do it is we feed the neural network, we train it on simulated images, which I'll talk about how we get those in a minute, and then labels. And then once it's trained, then we feed it experimental data, and it outputs predictions for where the defects will be. And since there are 4 types of defects that we're expecting, we train 4 neural networks to do each of the 4 different types of defects. In this process, the most important part of it is really giving it the training data. And training data in any sort of supervised learning consists of what we call input-output pairs. And in this case, the input pair, input-output pair is a simulated image. So this is not a real experimental data, but a simulated image. And then an output, which is a 2D map that has basically these white pixels wherever the defects are. And then on the back end, once we've trained the neural network using this input-output pair, then what it will do is when we feed it experimental data, then it will give us a similar map where the white dots represent the probability that a defect is present in each pixel. Okay, great. And getting this training data right, so by right, I mean making training data that matches your experimental data and also carries all of the types of variations that you would expect that data to have is really important. And so what we say is that the training data needs to be as close as possible to your experimental data in lots of aspects, including ones that as a human you would think are really trivially related. So things like the size of the image and the orientation of the image are really important, as well as things that are more difficult to match, like the signal to noise ratio of the image and any like experimental distortions or jiggles or anything else. And so as an example of that, we've trained the neural network in this case to recognize the image only at a particular orientation, so at what we call angle equals 0. And then if you then test the data, the neural network, while you on different copies of this image that have just been rotated, you can see in this output these bright dots where it thinks the defects are kind of blinking in and out. So basically, as we just turn the image, it loses the ability to find all of the defects. You can see this in this plot of defect number versus angle. And so the moral of this story is that if the training set doesn't really contain all of the variation that is present physically in your data, you're going to overfit your learning model and it's going to perform really poorly. So when we started doing this work back before generative networks were implemented, we tried to figure out how we could match our experimental data as well as we could. And so what we would do is make simulated STEM images that are noise-free and perfect, as they often are. And then we would try and degrade those images as much as we could until they visually matched our experimental data. And so we take the outputs of our conventional image simulation code, and then we do things like shear the image to replicate sample drift, rotate the image because we don't always load the sample at the same orientation, add noise and jittering, and then we even had to add non-uniform brightness haze to our simulations because our samples sometimes have carbon contamination on the surface, and that will show up as this bright haze. And so we did all of that, and we finally could make a simulated image that looks like this, that looks reasonably comparable to experiment. Okay, so we finally thought, okay, we have a good set of training data. We can go ahead and train our neural network. And these data, those training data, were sufficiently good that we had a hard time knowing which data was real and which was experimental. So the experimental image in this case is on the right, the simulated data is on the left. I think if I stared at these for a long time, I could tell you that this is the real data and this is the fake training data. But they're similar enough to distinguish that it's difficult to distinguish by eye. And usually that's a pretty good metric of what will be worthwhile for the neural network. So we take this data, we train up our neural network. We do that, like I said, 4 times for each of the different types of defects. And then once we're done, we can feed it experimental images, and it gives us these plots of where each type of defect is. And we actually tried to quantify how good this is by comparing it against humans. And we basically found that it was doing as well as the humans, but a lot faster. And in some cases, it was even more accurate than the humans, in that a human might not mark that a defect was there, but once the computer told it it was, then a re-examination of that same data, the human would be like, oh yeah, I missed that one, oops. And you can quantify this using these things called recall, precision, and F1. These all have pretty straightforward ways of calculating. Basically, TP is a true positive, FN is a false negative. So a recall, it tells you about how many of the defects you actually found, what % of the real defects you found. And the precision tells you about if you find a defect, what's the probability that it's correct. And you can see all of these numbers for the different defect types are extraordinarily high, so like high 90 percentile. And so that's what I mean by it's doing comparable, if not better, than a human could. So once we have this neural network trained up, what can we do with it? And the first thing you might say is, well, you can go through and find all the defects in the material. So we looked at what I would call now a relatively small data set, so 780,000 atoms. And we found 4,922 double tellurium substitutions, 27,082 single tellurium substitutions, 6,967 chalcogen vacancies, etc. And I can't tell you how wild it is to be able to get numbers like this for 2 reasons. One is that just finding this number of defects would be impossible to do by hand. And honestly, difficult even to do with any other data, non-AI type of data processing method. And then in addition, we can find extraordinarily rare defects this way, right? So this double chalcogen vacancy, there are only 141 of them in this many atoms. We found even rarer defects. For example, we found tungsten vacancies. There were 46 of these. So that literally is a needle in a haystack. And there's been a lot of discussion and controversy about whether tungsten vacancies are really prominent in any of these different types of growth methods for 2D materials. So it's pretty exciting to be able to go through and actually even count defects at this scale. But we can also use this ability to scale to really large atom numbers to push forward what we can achieve with electron microscopy in terms of precision. And what I mean by that is we can do something called class averaging. So we can take a STEM image, find all of the defects, and isolate the same type of defect. So in this case, it's the SET, so a single tellurium substitution. And then we can section the image so that we isolate all the copies of those tellurium substitutions, and we can sum all of that data together. And by doing so, we can generate these really high quality images. So you can compare this one to this one over here. You can see this one's a lot less noisy, and it's a lot easier to see that there's a tellurium atom here, whereas in this one, you probably can't tell by eye. And this isn't anything special or revelatory in that everyone knows that as you sum images, sum more and more images, your signal to noise ratio should get better. But what's perhaps not obvious to everybody is that as your signal to noise ratio goes up, the precision to which you can measure where an atom is gets better as well. And so when we go from one image to a stack of 200 images, we're also able to take the precision with which we can measure where all the atoms are down to the sub-picometer length scales. So here we're hitting about 0.3 picometers, whereas in a normal image like this one over here, we're looking at probably more like 10 picometers. People have been doing sub-picometer precision measurements of materials in the STEM for a while now. So this is a paper from Paul Voiles' group in 2014. It's really a valuable way to look at strain within a material. In this case, these arrows are indicating the strain at the surface of a nanoparticle. And the way people normally do it is they take a lot of fast images of the same object and then register those images together to improve the signal to noise. The fast imaging is to minimize distortions from like the sample drifting around. And then the summing gives you that high signal to noise so that you can measure where the atoms are. But when we try to do that sort of thing in a 2D material, we basically can't copy this method because you can't dump enough electron dose in the material to get a nice image without also making these giant holes in the system. And so rather than doing that, we can borrow this idea from cryo-EM, where they take a lot of images of the same object, of nominally identical objects, instead of taking one great image of one object and then average them together. So that basically is what we're doing now with the neural network. We're taking we're using the neural network to find single instances of these single atom defects, summing them all together, and then making these nice class average images where you can really see a lot more detail than you can in any individual given image. And just on its own, this class averaging approach is pretty valuable. You can see here that if we stack all these different images together of different defect types, the defects are all located right here where my pointer is. But if you look at the next atom over, as we scroll through the images, you can actually see that atom moving, shrinking in towards the defect. And that actually, what you're seeing with your eyes now is a strain field due to a single atomic defect in our 2D material. And you can extract that quantitatively once you have your really high precision image. So over here, we have this vector map. So these vectors have been enlarged so that you can see them, but you can directly visualize the strain field around this individual vacancy. Whereas if you try to do that in our original single image, you just get trash. Okay, and we can repeat that on all of our different types of images, defects. And you can see indeed that when you replace selenium with tellurium, the lattice expands, whereas if you have a vacancy, the lattice contracts. Okay, so that seems great. We wanted to now take that approach and really just scale it up. And once we tried to scale up our neural network, this is when bad things started to happen. So I showed you before our recall precision and F1 scores, all kind of like 99% for the single vacancy. That was great. It turned out when we tried to replicate that with these large million atom data sets, those numbers got really bad. So when we were using this approach where we tried to manually replicate the experimental conditions and then feed in really large data sets, you can see our recall and precision started to drop. And so, okay, so we tried one data set and we got those numbers kind of around 90%. We tried another and some of our recall numbers got as low as 66%. And this was quite worrying. So you might think, what is happening? Are you guys just suddenly bad at machine learning? The answer is no. The reason this is happening is that our larger data sets aren't just the same as small data sets. Once you're feeding in these data sets where it's like 200 images, for example, you're taking data over a long time. And when you do that, the optical conditions and other types of conditions in the microscope will drift. So this is an image series as we progress over the course of 9 hours. And really what's happening is that the spherical and other higher order aberrations in the tool are kind of drifting away from perfect. And so you start with a nice clean atom where you can, nice clean image where you can really see all the atoms to getting pretty hazy at the end. And this, so unless you have the ability to just have a rock stable microscope, you can't really, there's a physical limit to how well you can just expand your data sets. And this is where generative AI really came to the rescue for us. So we started using these tools called CycleGANs, or cycle generative adversarial networks. The idea behind a CycleGAN is it's going to learn and transfer some sort of, they call this like a style transfer. So similar to adding a Monet flare to a llama image. What the CycleGAN is doing is it's adding an experimental flare to our simulated data. So what you do is you train the CycleGAN to recognize experimental data. So you just feed it a bunch of experimental STEM images. And then once it's trained up, you feed it a simulated image that doesn't have to be very faithful now to your experiment. And what it will do is take that simulated image and add this experimental style. So instead of us guessing what amount of shear or rotation or whatever noise has to be in the simulation, the CycleGAN adds that all for us. So it turns this simulated image to an experimental like realistic one. And a couple of things are important here. One is that this really gives you the ability in simulations to replicate the conditions of any experimental run. So if you've got a well-aligned microscope, the GAN can generate experimental-like images that are really for a really great, well-aligned microscope. And you can also tell it, hey, my microscope parameters were crap today, and it will very faithfully reproduce those as well. And it really does so without changing the atomic structure. So if you put in a simulated image with these two defects right here, you can see they have appeared again over here in our experimental-like data. The way that this works, okay, so now we have a new workflow. Instead of having to manually degrade all of our simulated data, we now let CycleGAN do that for us. So we have this code to automatically acquire the data. We feed that experimental data into our CycleGAN to train it. And then the output of the CycleGAN, those realistic images, those are what we use now to train another AI, a neural network, the FCN, to recognize where the defects are. So really what we're doing is we're using the CycleGAN to generate training data so that our AI, our FCN, can recognize the defect positions better than when we were doing it manually. And in this process, it's really critical to use not just any generative network, but something like CycleGAN that preserves those atomic locations and defect positions. And so, and that's important because in our training data for the defect identification model, you need to have those input-output pairs. So you need to know where all the identities of the defects actually are. And that's what the cycle part of the CycleGAN actually does. So I don't want to go into too much technical detail here, but this is the actual model behind our CycleGAN. And you can really just think of the CycleGAN as doing a series of transformations between domains. So the domains here are the experimental domain and the simulation domain. And it's moving back and forth images from one to the other, while minimizing the loss, right? So minimizing the differences between the experimental-like data in both real and reciprocal space. And so I'll talk about the reciprocal space thing in a moment, because we implemented this kind of unusual structure where the CycleGAN is looking at the image both in real space and in Fourier space. It's reciprocal, the Fourier transform, and comparing both those in experiment and simulation. And the reason we did this is because, frankly, when we only let the CycleGAN look at the images in real space, it did a bad job in generating new images. So this is an unrealistic simulation. This is the raw input to the CycleGAN. And this is what happens when we ask CycleGAN to give us an image of graphene without the FFT like part of the CycleGAN. And you can see all these weird lines in the Fourier transform. Those shouldn't exist in experiment. And that was a dead giveaway that this wasn't real data. But when we added this kind of FFT discriminator, it started giving us much more realistic images, even in real space. And then I really enjoyed Fourier transforming these things because I started to see spots like this, which if you were to show me this data and not tell me it wasn't real, I'd tell you 100% this is an experiment, and that you had some source of electrical noise in your TEM room messing up your image. And that's why you're getting these 2 extra spots in the FFT. So, so once we actually put in this extra level of FFT discriminator, the CycleGANs got basically scary good at being able to make realistic looking STEM images of whatever structures we wanted to give it. And we actually fed it a couple of different material systems to give us images for. So we actually did go through and quantify how good these CycleGANs are. Basically, we calculated a couple of different numbers. This is the KL divergence down here, for example, and you basically want the smallest KL divergence between whatever your simulation is and experiment. And you can see of these numbers, CycleGAN is the lowest. So in all of these different metrics, CycleGAN is really replicating our experiment really well. But of course, you don't have to take my word for it. The most impressive, I think, ability to fool is for if a GAN can fool a human. So here are 6 images of different materials. There's graphene, there's tungsten diselenide, and there's strontium titanate. And some are real and some are fake. The top is the images and the bottom are the Fourier transforms. And I'll just give you a minute to see if you can figure out which one is which. Okay, so here are the answers. Every other one is fake. And so you can see that we really have a model here where you just chug, feed it your experimental data, and it teaches the CycleGAN to make simulations that are really realistic of whatever type of data you fed in. Once we started using these CycleGANs to train the models rather than manually training the models, we got a lot better precision. So, and actually, you'll see if you compare these two, that overall the numbers have gone up a little bit in terms of recall, precision, and F1 score. But to me, what's important, just as important, if not more important than having the absolute numbers be high, is having it be relatively reproducible. And so you can see all these numbers are more similar to one another than here, where we're just getting this like freakishly low recall for no apparent reason. And so this CycleGAN is not only better able to represent the data and train a neural network to recognize defects, it can do so more reproducibly and with a lot less manual intervention. So if you go back to our original idea, this is really the type of thing that we need to make that STEM of the future. So what we've done, to sum up my talk, is we've taken this idea of generative AI, used it to generate realistic STEM images, which we turned into a method to train a high accuracy and yet adaptable machine learning model to recognize atomic scale defects. And so this really fills in that last part of the STEM of the future, this ability to process and recognize interesting features. And so I hope it will one day become the part of the model for how we operate and really extend as humans our ability to do science at the atomic scale. So here are a few resources if you're interested in learning more about our work. Our CycleGAN work was just published in MPJ Computational Materials. We have our older paper in Nanoletters just using that conventional neural network that was trained with the manual simulations. And then our codes, for example, to acquire TEM data automatically and to do the ML stuff are online on GitHub, and our raw data for this latest paper is on Zenodo as well. So with that, I'll just mention, one more thing, that we have this graduate trainee program called DigiMat for materials and AI. The program is actually wrapping up in the next couple of years, but we're still sending out students every summer to do internships, including at national labs. So if you're interested in this, please feel free to let me know if you'd like to host one of our students who's already trained in this exciting area. And then I will thank all the wonderful people who worked on this project and my research group, and then all of the people who fund us. So thank you, and I will take any questions.
Thank you very much, Jane, for the great talk. I want to open it up to questions from the audience. So